All right, let's talk about something that's probably going to change the way you experience the world around you forever. We're going to dive into a massive misunderstanding most of us have about physics, specifically the idea of heat. If you stick with me, you're going to walk away with a brand new thermal intuition.
So, let's kick things off with a puzzle you've probably wondered about your whole life. You walk into a room, right? You put your hand on the wooden door, and then you grab the metal doorknob. And that doorknob feels way colder. But how can that be? They've both been sitting in the exact same room for hours, in the same air. They should be the same temperature.
And here's the big reveal that just messes with your head. They are. The doorknob and the door are at the exact same temperature. So, that's the central mystery, isn't it? If your sense of touch isn't telling you the temperature, what on earth is it actually telling you?
Okay, this right here, this is the single most important idea we're going to talk about. Your skin is a bit of a liar. It doesn't measure temperature at all. What it really measures is the rate of heat flow. The feeling we call cold is just the sensation of heat leaving your body quickly. And hot, that's just the feeling of heat rushing into your body.
Now, to really get this, we have to fix our language. See, we all kind of throw around three words: temperature, thermal energy, and heat, like they all mean the same thing. But they don't, not even close. So let's untangle them, one by one.
First up, temperature. I want you to forget about how hot or cold something feels for a second. In physics, temperature is just a measure of how fast the tiny little particles inside an object are jiggling around. That's it. A high temperature just means the particles are having a wild dance party. A low temperature? They're just doing a slow waltz.
Next, we've got thermal energy. So, if temperature is the average dance speed, thermal energy is the energy of the entire crowd on the dance floor. It's the total energy of every single one of those dancing particles added together. And that means the amount of stuff you have, the size of the crowd, matters a lot. And this is where it all clicks. Think about a small cup of boiling water. It has a really high temperature, right? Its particles are moving incredibly fast. But now, picture a huge, warm swimming pool. Its temperature is lower, but it has way more thermal energy, just because there are trillions and trillions more particles in it. The pool's crowd is absolutely massive, even if they're all dancing a bit slower.
And finally, we get to heat. Now this is the big one. Heat isn't a thing that an object has or contains. Heat is a process. It's the name we give to thermal energy when it's on the move, flowing from a place with a higher temperature to a place with a lower temperature. It's just energy in transit.
So, with our new, sharper vocabulary, we can finally crack the case of the cold doorknob. To do that, we just need to understand how this invisible river of heat actually flows from one place to another.
Turns out, heat gets around in three main ways. There's conduction, that's heat moving through direct touch, like when the handle of a spoon gets hot in your soup. Then there's convection, where moving liquids or gases carry the heat, like steam rising from a kettle. And finally, radiation, which is energy traveling in waves like the warmth you feel from the sun, even across the vacuum of space. And there it is, our answer. The doorknob mystery is all about conduction. Both the wood and the metal are colder than your hand, so when you touch them, heat starts flowing out of you. But metal is a fantastic conductor. It's like an energy superhighway. It yanks the heat out of your hand incredibly fast. Wood, on the other hand, is an insulator. It sips that heat away very slowly. Your brain just interprets that rapid heat loss as, whoa, that's cold.
Okay, so now that we've got the basics down, let's use our new thermal intuition to solve a couple more fascinating and, frankly, painful everyday puzzles.
First up, let's talk about heat sponges. Some materials, like water, are amazing at soaking up huge amounts of energy without their temperature actually going up all that much. The scientific name for this is heat capacity. You can think of it like this. Pouring a cup of water on a rock makes the rock's surface wet right away. Pouring that same cup on a sponge, well, the sponge just keeps absorbing.
And this explains the dreaded pizza burn. The crust and the cheese came out of the exact same oven, at the same temperature. But the dry crust is like a heat rock. It has a low heat capacity. The cheese and sauce, full of water, are heat sponges. They stored up a ton more thermal energy. So when you take that first bite, the cheese dumps all of that stored energy right onto the roof of your mouth while the crust is totally fine.
Now for an even weirder idea, hidden energy. You know, sometimes you can pump energy into something and its temperature won't go up at all, not one bit.
Why? Because that energy is busy doing something else. It's changing the substance's state, like melting ice into water. This is called latent heat. If you stick a thermometer in a glass of ice water, it will read exactly 0 degrees Celsius until the very last sliver of ice is gone. All the incoming heat is being used to break bonds, not to speed up the dance.
You can feel this right now. Seriously, lick your finger and blow on it. It feels instantly colder, doesn't it? That's latent heat in action. For the water on your skin to evaporate and turn into a gas, it needs energy. And where does it get that energy? It steals it as heat directly from your skin. That rapid death of heat is what your brain registers as a powerful cooling feeling.
So let's put this all together. The world you feel isn't exactly the world as it is. Pretty much everything in the room you're in right now is at the same temperature. The difference you feel is just how fast you're trading energy with those objects. So here's our new mental model, the big takeaway. Temperature is the average speed of the particle dance. Thermal energy is the total energy of the whole crowd. And what your skin feels, that's just how fast that crowd is either crashing into you or running away from you. So the next time you touch a cold piece of metal or burn your mouth on some hot pizza, you'll know the real story. Your skin is just a detector for the flow of heat, not a thermometer. And that kind of makes you wonder, doesn't it? Now that you know your skin is lying to you, what else in your daily life feels one way, but is actually something completely different?